Hello, IBSL2. Today you guys are actually going to start talking about Trig. And Trig is one of the units that we really need to review before we start into the calculus. We are going to have to know it backwards and forwards, front and back. So if we have not already taken time to review our sine, cosine, tangent, today is the time that we're going to get a chance to do that. So before we start that, I'd like to take you into our Pythagorean theorem. And I want to take you guys back to geometry a little bit, and also SL1 when you guys spent some time with this when you first were introduced to trig. I want you guys to think back to that right triangle. And the right triangle plays a major part when we start looking at the unit circle. In Pythagorean theorem, Pythagoras was saying that the length of this side A, or AC in this picture, if you square that length and you add it to the length of CB squared, so this blue square here plus this green square here, you should get the equivalent of this red square here, which is the length of the hypotenuse squared. And I can drag this triangle to make it as big or as small as we want to make it, and no matter what, Pythagorean theorem holds true. Okay? It's still going to be a right triangle whether I change the side length of AC or whether I change the side length of CB. Still holds true. Little history about Pythagoras. So anytime that we look at a new topic, just take a moment to read through this. So when we're thinking about why do we learn the Pythagorean theorem, why was it even invented, what different areas does it actually fall into? If you notice here, there are a lot of different ones that we probably don't even think of. So take a moment to read through this and make a few notes for your own notebook. And remember, since we're on a video, you can push pause and you can take as much time on this page as you need to in order to complete your notes. I'm going to take you over here though. If you guys look along the bottom here, there have been all kinds of different people who have actually studied Pythagorean theorem and worked with that same exact idea and tried to prove it in different ways. We're going to look at Pythagoras' proof just because it's very visual and geometric for us. So if you guys take a square, Pythagoras said if you start with a square, and let's just label the sides A and B. So what we're saying is that line segment A and line segment B added together make the entire side length. And the length of A is going to be the same on all four sides, as is the length of B. What he's saying here is if you try to make a right triangle with A and B as your legs, how can we do that? Well, if I look here along this line segment, if I try to make a triangle with this A and this B, I can't make a triangle. It's one line and then I'm going to make another line. I can't make the three different sides. So my option here is to make A here, this one of the legs, and B one of the legs. That means my hypotenuse would be this connection here from A to B. If I do that with all four sides, I get something that looks like this. And as with any proof, when you guys are working through, if you create a new piece to your picture, we have to label it. So now we have the side C that's labeled. Well, if you guys notice, this is going to be the same triangle on each side, since we've already talked about how A and B are the same length. So that means C is now going to be the same length. What property is that that says if A is the same as A, B is the same as B, then C should be the same as C? You guys peek over here, you've got the transitive property, okay? Then he said, well, let's look at it backwards. What if we express the same area but using subtraction? Okay, so if I take this area here, really the way I got it was by doing the entire area of this big square we started with, and what do I have to take away? Yep, so I'm going to take away my four different sides, all right? My four different triangles. So if I say that this C squared here in the middle is really the original area of the square and minus the four smaller triangles, I get the white area that's left over, okay? We're going to duplicate this square, and these triangles are now loose. Well, another way to look at it is if I kind of move these triangles around a little bit so that these two wind up lining up with each other, and these two wind up lining up with each other. okay? These are the same 4 triangles that I had over here in this original square. But by me moving them around a little bit, what do you guys notice about the area here and the area here? So if this is A, and this side now is A as well, since this is B down here, what's left over is the A part. This is A squared. Similar thinking down here, if this is B, then this must be B, since over here, this would be B, because that part's the A part. This is B squared. So now this white area that was C squared in this picture becomes A squared plus B squared in this picture, all right? So why are we spending so much time on Pythagorean theorem? Okay, what we're gonna have to start to think about is where all of this actually takes us. And you guys, last year in SL1, started to talk about the unit circle. And when we're talking about a unit circle, we're saying that this little point is starting to travel. It starts at 1, 0. We call it a unit circle because this length is 1, the radius is 1. This point starts to travel around the circle, and we can stop it at any point along the circle. What's going to start happening is this y distance is going to be your sine value, and this x distance is going to be your cosine value. Our radius continues to be 1 in this example. When you guys are looking at your different triangles, okay, we were talking about right triangles the entire time. Right triangles, because later on our very first identity is the Pythagorean theorem with sine and cosine. If I take this and I change b, so my y value is changing. What is also changing if I change my y value? Look at that angle, look at theta for a moment. Okay, my theta definitely changes as well. So as y gets taller, my theta changes. If my theta changes, then look at that. All 3, sine, cosine, and tangent, are all changing as well. This is what's happening to your triangle as it is traveling around the circle. So if we look back at the unit circle, imagine that happening here as I drag this point around. I'm changing the y value. I'm changing how high, how tall this triangle actually is, which means that my x value also changes, my angle changes, and my sine, cosine, tangent values also change, depending on where I am around the circle, and then also down in quadrant 3 and 4, the same thing happens. So let's take a peek at if my A value changes. So let's say I pull this A out. Notice my B and my A are both changing. Well, since it's proportional and all 3 sides are changing, notice what is not changing right here, that angle. So you guys learned that similar triangles, right, they have the same proportion. So if I'm going to change my side lengths, and they're all proportional, my angle doesn't change. Well, notice what happens to sine, cosine, and tangent. This is why we talk about a unit circle. A unit circle is 1 radius, and it's nice and easy to work with because of the radius is 1. But I can make that radius any size I want to, which is what I'm doing right here. If I tried to fit this triangle inside the unit circle, well, I'd be busting out of my unit circle right now. I'd have to make a much bigger or smaller unit circle. So I can now think about my circle going around this much larger triangle, but it doesn't matter because the unit circle is proportional to any size circle. So that's why we like to talk about it as a unit circle. It can be any unit you want, but it's very easy to work with if we have 1 as our radius. So when we're looking at this picture and we're trying to put our triangle inside, we're starting to notice that, hey, this actually makes sense and it's easier to work with when the radius is 1. So what you guys have to worry about is the sine and the cosine values. So let's take a peek here. You guys know this from last year. If you don't, please make sure this is jotted down in your notes. Opposite leg over hypotenuse gives you your sine of theta. What do we mean by this? Well, if you're standing right here on theta, the opposite to theta right now is BC. So the opposite side length is literally across the triangle from theta. Your hypotenuse is always opposite the right angle. Cosine It says the adjacent leg is opposite the hypotenuse. My adjacent leg right here is AC in this picture. That's your adjacent, and we put that divided by your hypotenuse. Again, think about how these are changing as this point is traveling around the circle. Tangent is your opposite over adjacent, also known as your sine divided by cosine. Those values equate to this proportion here. So sine is opposite of this angle divided by adjacent, which is right next to it. It's adjacent to this angle. Okay? Take a moment to look at your notes and make sure you guys have a couple things written down. First of all, some history. Make sure you've got some historical context. What was it about trigonometry? What are we doing with trig? What are we doing with the Pythagorean theorem? Who made it up? All right. Right triangles. There are two specific right triangles that you guys are going to need to make sure you have. You're going to need to know your 30, 60, 90 triangle. So if you haven't already drawn, much neater than the way I am right now, make sure it's a right angle and make sure that one of the angles is 60 degrees and the other is 30, and you have your 90-degree angle right here. I'll grab another color. So now you guys have 30, 60, 90. Well, so remember your radius is 1, and I'm going to come over here and grab blue. So if our radius is 1, that would make, the way I learned this in high school was it's easy to remember one number at a time. So opposite 30, we put the value of 1 as a side length. Opposite 60, we made the value of square root of 3. Opposite 90, we put 2. Those are super easy to remember. 1, square root of 3, 2. They're in increasing order, right? 1's the smallest, 2's the largest. It's also the longest side. But if you go through and divide by 2, all right, as long as we do it to all three, it's proportional, then this becomes your 1. So 90 degrees, sine at 90 degrees makes 1, right? And sine at 30 degrees makes 1/2. And sine at 60 degrees makes square root of 3 over 2. So that's an easy way to remember it. You guys can do the same thing with your 45, 45, 90 triangle. So your second triangle that you've got to know, again, label it with the 90 degrees. Make sure that these two angles now are even, and they are both at 45 degrees. The way to remember that one is if you guys have your two side lengths again, we want to make them 1, 1. If you do the Pythagorean theorem, 1 squared plus 1 squared, you guys will get square root of 2 when you solve for that. And you have, well, how do I wind up getting rid of this? Okay, divide through again by my hypotenuse. So I've got 1 over square root of 2 for sine of 45. I've got 1 over square root of 2 for cosine of 45. And then I have square root of 2 divided by square root of 2, and I now make my 1. Okay? So when we're talking about tangent of 45, when you do sine divided by cosine, we get 1 as well. Okay? So again, we've been talking about Pythagorean theorem. We know a squared plus b squared gives us c squared. We know that a and b are the legs of triangles. C is the hypotenuse. We also talked a little bit about just your basic trig functions. So we're saying sine theta, that's cosine theta, that's tangent theta. Okay, if these are all defined as opposite over hypotenuse, and so on and so forth. We had this on the other screen. Make sure you guys have these three written, and then also think about your cosecant. Think about your secant, opposite of cosine, and think about your cotangent, opposite of tangent. Okay? Take a minute to fill all of these 6 in so you guys have them all written down. And while you're finishing that up, if I gave you guys this example here, and let's say that our right angle is here and our theta is here. Take a minute to figure out, well, first of all, find the last side, and then also go ahead and write up sine, cosine, and tangent.